So today, Shivam and I will discuss about the efforts of the Synthetic Observation Working Group, specifically to try to model both mock galaxy surveys and CMB maps. So this talk is really brought to you by a bunch of people, not just us. So here you see the PIs of the Synthetic Observation Working Group, us, and then the PIs of the Connections Working Group, and then the members of the Synthetic Observation Working Group, and some members of ILI that lately have been working also on some amazing projects very closely. Okay, so just a reminder of why we're doing all of this. We have heard a lot from Laurence and from Greg of what's the big scope of the collaboration, but ultimately what we want to do is to do inference to try to constrain both astrophysical and cosmological parameters from observations. So what we start from is our initial condition, a cosmological model. And so we have our dark matter assembly history and our dark matter density field. So what we do is then add baryonic physics and feedback physics, so essentially our galaxy formation model, which adds a new layer of parameters. And then what we care more for in this group is really the synthetic observation layer, so how to move from the theory space to the more mock observable space, which adds extra parameters, which are emission and attenuation related parameters. What we then also need to add is an observational layer, so we need to account for the filters of whatever instrument we are trying to mock observations of. We need to account for noise and response functions. And ultimately, we feed all of this into the ILI pipeline, so in the implicit likelihood inference pipeline. And what we try to obtain is to attain joint posteriors on all of the parameters that we input, so cosmological, astrophysical, and emission parameters. And a portion of all of this has been done by previous works, but I think what is really the unicity of our collaboration, uniqueness, yeah, okay, whatever, that is that we try to do everything all together. And we have really put together a group of people with diverse expertise on each of these fields so that we really try to learn as much as possible of the universe. But ultimately, we also want to do real observations. And so this is another bit that I'm not going to focus on as much in this talk. But ultimately, we also want to do inference on real observations and constrain, again, the same set of parameters. So what are these observations that I'm talking about? This is a very nice movie from, actually, we cannot really take credit for it. It's from the Planetarium of the University of Chicago. But I think it's really nice because it summarizes the two big observation sets that we're using. And one is the SDSS Galaxy Survey that provides us with optical images of thousands of galaxies in the local universe and some quasars up to Redshift 2. And then also CMB sky maps from the ACT telescope that Shivam will discuss more in a second. So I'm going to now move the talk to the more galaxy side of the Synthetic Observations Working Group, and then Shivam will take it away and discuss the CMB applications. Okay, so I was showing this scheme before, and I was saying, so we start from dark matter-only simulations, then we have our galaxy formation model, and then we want to arrive to our synthetic observations layer. So I want to spend a few words on the first two bits. So what are these simulations that we're using and trying to make mock observations of? And these are mostly thanks to Shai, Paco, and Danielle, and these are based on camels. So we have two sets of the simulations. One is Camels Hydro. So this is dark matter simulations with then Hydro simulation on top. And what is amazing of Camels is that we can really have different realizations of cosmological boxes where we are changing both cosmological parameters. Specifically, we will look into omega m and sigma 8, but also several astrophysical parameters, such as the strength of supernova feedback or AGN feedback. And then we can also swap different galaxy formation models, so we can really try to see how a different realization of the universe can change when we change all of these different knobs that we generally keep fixed when we are doing one single simulation effort. So in this case, when we have the Hydra simulation, the box is relatively small, it's 25 megaparsec. And that's why we also joined this effort with another one, which is Camel Sum, where we use a bigger box. But in this case, we don't also run Hydra simulation, but we use the Santa Cruz semi-analytical model developed by Rachel and collaborators to essentially do the galaxy formation modeling bit on top of the n-body simulations. And again, also in this case, we can do a broad sampling of many galaxy parameters together with our cosmological ones. And in this case, we have a bigger box, which is 100 megaparsec cube. And you can see all the people involved in this effort here. And also, I believe Shai will discuss some more about this in his talk. Okay, but so this is synthetic observation, so let's move to the synthetic observation layer. And the tool that we decided to use to produce this synthetic observation is Synthesizer. So Synthesizer was developed by Chris Lovell, Steve Wilkins, Will Roper, and their collaborators. And it's a fast and flexible Python-based pipeline to generate mock images and spectra for galaxies, starting from analytical models or simulations. So this is kind of a scheme to show the capabilities of Synthesizer. So what Synthesizer really relies on is grids. So we have grids of stellar population synthesis models and AGN models that are then run through photoionization codes. And then they are combined together to make a galaxy object and model its emission based on 3 key components within each galaxy, which are stars, gas, and black holes. And this is, okay, so our pointer. So this is what I'm talking about here. And ultimately, we can also account for extra effects, for instance, the effect of dust that we'll also focus on a lot at the end of the talk. And ultimately, what we get out of Synthesizer, there's many different options. So we have line collection, and so in this case, we get line profiles, so we can do full width al maximum and line fitting, or we can do actual spectra, or even spectral cubes, and mock images of our galaxies, so spatially resolved images of our galaxies. And Synthesizer already has some instruments that are built in. So with the noise model, the filters, everything ready to use in the available package. But it's, as I said, a very flexible and easy to use pipeline. So anyone can add whatever instrument they want to add, whatever wavelength and filters they would like to change this up with. And this was presented in this paper by Chris, which has recently been published. OK, so here is an example of application. So this is Synthesizer applies to Camel's Hydro. So here you see the spectra of one of our galaxies divided in different components. Here behind, you see the attenuation curve that we have assumed, which in this case is a fixed attenuation curve, a Milky Way-like. Again, we're going to discuss this more in a second. And below here, you see some of these filters that I was mentioning for some of the built-in instruments that we have in Synthesizer, which are essentially Galax, SDSS filters, and then KIDS. So here are some of the details of Camel's Hydro. And what I really want to stress is that we are looking at 34 snapshots, spanning the redshift range between 0 and 6. So we are really doing like 100 millions of galaxies, again, changing galaxy model, changing astrophysical parameters and cosmological parameters. And this is work in progress. So we are doing now the same with Camel Sum. For now, this is what you're seeing here. These are luminosity functions without dust, but this is an ongoing work in progress. So essentially, everything I'm going to show in the following is going to be based on Camel's Hydro, but then we will produce the same for Camel's Sum. OK, so what are we producing with Camel's Hydro? These are 2 examples of things that we have looked into. And one is luminosity functions that you see in these first 2 rows. It's 2 different bands, far UV and R band. And here is color distributions that you can see here. And the different colors, so first of all, the different columns here are different galaxy models. Different colors are different values for now cosmological parameters. And as we move on in this animation, you will see changing also astrophysical parameters. And the dashed black line that you see is actual observations. So what is cool is that, again, as I said, we can really look at the effect on luminosity functions or color diagrams of changing. I was changing now cosmological parameters, and now we're looking at different, for instance, supernova feedback efficiencies, and now AGN feedback efficiencies. So we are really looking at how models change observables in real time. But just looking at it, it's not maybe very helpful or very quantitative. So what we want to do ultimately is to do inference on it. So I believe Matt will discuss more about the inference details of this, but I'm going to focus more on what we have learned in terms of the physics. And here you see essentially what's happening when we try to constrain both our cosmological parameters, our supernova feedback parameters, and AGN feedback parameters for different galaxy models. So the changing color that you will see is changing galaxy model. I'm going to switch through all the ones that we have looked into. I'm going to finish with Illustrious TNG because this is a bit of the template model that we used within the collaboration. And I think that one result that was really interesting and a bit surprising maybe for us was to notice that from luminosity functions and color diagrams, apart from constraining supernova feedback parameters, which maybe is not so surprising, we actually get pretty stringent constraints also on omega matter and sigma 8. I made AGN parameters transparent here. We don't really constrain them, but this is not so surprising because we didn't really use any AGN observables. So this is something that we want to do in the next iterations of LTU. And again, I believe Matt will say something more about the inference pipeline. OK, so are we done? Is this everything that we have produced? Well, I kind of glazed over something that is very annoying, which is dust. So there was, for anyone who was at the panel discussion yesterday, panel discussion started with dust, ended with dust, and there was the usual question of why should we work on dust? Should anyone work on dust? Well, I work on dust, so now you will hear about it. So first of all, I showed the usual slide on to try to convince people why dust is important and why should anyone think of it. And essentially, the reason is that dust really changes the photometry of galaxies, so the actual observables of galaxies. Here's a simple example. This is a local galaxy, M82, for which we have beautiful multi-wavelength images. And here you will see some modeling efforts, and the white points I want to stress are actual observations. OK, so if we only account for stellar emission, this would be the prediction that we would make for this galaxy. So you can clearly see that we are missing the observation, both on the longer wavelength side and on the very short wavelength side. And this is exactly because we are missing the effect of dust. So the effect of dust is twofold. On one hand, dust grains attenuate a portion of the stellar emission, and this is what is shown here by this new red curve. And how we quantify this change is through the so-called dust attenuation curve, which essentially are the logarithm of the ratio of what would be the actual intrinsic flux versus the observed one, well, the other way around, whatever. And then this is what we really care for. This is the bit that we care for in modeling when we are doing mock galaxy surveys such as the SDSS, because again, SDSS and Galaxy, because we are looking at UV and optical bands. But this is not the only effect of dust. There's also an active effect. So these dust grains have absorbed this radiation. So of course, they get heated, and they re-emit this radiation as thermal radiation in the infrared and far infrared wavelengths. And this bit we haven't looked into as much for the galaxy side, but this is actually very important for CMB sky maps because this is something that needs to be cleaned and eliminated when we're looking at CMB maps. OK, so what we have tried to do, we have tried to really model for now the attenuation part, so the attenuation curves of galaxies. And what we have done is to look at a very, very large number of galaxies from the TNG50 and TNG100 simulations, 6,400 galaxies. And these galaxies span a very broad range in terms of galaxy properties. So you can see here in stellar mass, SFR, and metallicity. And what we have done is to run the simulation through a radiative transfer code, which is SCRT, to essentially obtain the observed spectra. Here you see an example, and you can see that at the shorter wavelength, there's this scatter in what's the observed flux. And this is because for each galaxy, we have considered 51 line of sight, really trying to create the most complete library that we can have of synthetic attenuation curves to really try to understand if we have a given galaxy, what should be its attenuation curve and how should we correct for it. OK, so yeah, sorry, this should have appeared before. OK, so this is an example. This is the same galaxy observed through 4 different lines of sight. And something that maybe not everyone who works in dust appreciates is that really attenuation curves, even within a single galaxy, can change dramatically when you're looking at it through different inclinations. And again, maybe you don't care for attenuation curves, but if the attenuation curve changes, it means that also the spectra of the galaxy that you're observing changes. And this is exactly what we're showing here. So this is the same galaxy through 4 different lines of sight, and this is the corresponding attenuation curves. And something that I want to stress is that this gray shaded area that you see behind is actually the 1684th percentile range of the full distribution that we have considered. So if you pick some line of sight in an individual galaxy, you can span a wider range than the full distribution. Again, they are picked like exactly because we wanted to show how weird things can get. So it's not a very uniform galaxy, but sure, it's interesting. OK, so what you have tried to do then is to pick one of the functional forms that we have in the literature, a bit more, a slightly more complicated one, that one of the most commonly used one, because we were really trying to get as good of a constraint on this attenuation curve as possible, and try to fit the free parameters of these synthetic attenuation curves that we have obtained, again, with the idea that then we can provide this into our whole pipeline, so that if we have an intrinsic galaxy, you can say, OK, this is the attenuation curve that you should apply to this galaxy. So these are some results. This is the distribution of free parameters for our TNG local galaxy. And something that was maybe a bit surprising is, first of all, that we find, again, attenuation curves that are deviating a lot from just the Milky Way, SMC, or typical templates that are used. And we have used, for now, in this first work, we have used the Milky Way dust composition in terms of chemical composition and grain size distribution. But this absolutely does not imply that we obtain a Milky Way attenuation curve. Indeed, these are the distribution of values, these shaded histograms. Just as a note, the gray histograms instead are observations from SDSS. So I would say that we're doing a pretty good job in reproducing them. But what I wanted to highlight here now is that the values for a Milky Way curve are shown here by this black line. And you can see that in several cases, the black line is actually pretty outside of the distribution of our best fit values. But OK, so we don't just want to have a vague flat prior for our attenuation curve. Ideally, what we would want to do is to pick a galaxy from our model and be able to say that what would be the attenuation curve of exactly this galaxy, given its galaxy properties. So the next bit that we did in this paper that was published this year was to look for correlations between the free parameters of the attenuation curve and global galaxy properties. And specifically, we find that a major driver is the SFR surface density. And so we find this minimal set of scaling relations that are, again, derived based on the TNG post-process simulation. And so in different bins of sigma SFR for a given galaxy, we are able to predict what its attenuation curve should look like. And this is what you see here on the right. And ultimately, we have compared both with observations and with the actual synthetic attenuation curves. This is what you see here. So on the y-axis, you have the attenuation that we predict in various bands from our minimal set of scaling relations, whereas on the x-axis, you would have the true value of the attenuation. For the colored contours is from the simulations, and instead for the empty ones is from SDSS observations. So again, I would say even with this first simple effort, we are doing an OK job. But we were not super happy just with this. And we really like our ILI colleagues, so we decided to try to do something better. And so we have started a new cross-group effort, which is Syntops ILI project. And I'm very happy about this clip art. Maybe you don't know what it is, but these are the small dust specks from Miyazaki cartoons, and they are pasted on top of the typical machine learning scheme that you have. So what did we want to do with the ILI people? So we wanted to essentially chalk this functional form that we have used for the attenuation curves, because this is a bit based on, well, previous works, and I'm sure amazing thinking process from observers, but it's not super physically motivated. So what we wanted to try to do is to take our synthetic attenuation curves and run them through the information ordered bottleneck pipeline that Matt has developed, And the idea here is to try to really understand what is the minimal number of independent components that we need to describe an attenuation curve. So really just starting from scratch. And this is a preliminary result of what we find. And essentially what you're seeing here is the loss, so the loss of confidence between the reconstructed attenuation curve versus the true one at the beginning, and how it changes as we increase the bottleneck size. And essentially what you see is that as we go beyond 4 in terms of dimension, we are not really gaining any much more accuracy in our attenuation curve shape. So what we would guess from here is that we need 4 independent parameters. Now, what we want to do next is then to use symbolic regression to find the new functional form to really express this attenuation curve as a function of these 4 parameters or a combination of them. And this is what we have done with Daglan. So this is a first result from our symbolic regression efforts. So I'm going to walk you through it. This is the usual attenuation curve. You just see x rather than lambda because we have normalized it to the wavelength in the V band. And then the functional form that you see, so these B parameters are actually functions of our first 4 IOB components that we mentioned that are needed to describe the attenuation curve, whereas these A parameters here, these are actually constant numerical values, so these are going to be the same for our galaxies. Whereas these other ones, what we want to do next is to try to understand how they should be given observable galaxy properties. And here below, you see how this functional form is performing. So the solid line is always the true attenuation curve that the true synthetic attenuation curve that we input, and the dashed one is what we are predicting with our functional form. What we have also checked for now is what's the error that we're making on the attenuation curve, and we have compared with the other parametric forms that have been used in the literature. So the typical 2-parameter one with a single slope and a bump, and then this 4-parameter one that we were using before. And the red is instead our own effort. Again, this is preliminary, but you can kind of see already that we are doing at least as good as the 4-parameter one. And what we hope is that our model is really going to shine in the part where we try to connect to galaxy properties, because we have made a huge effort in making these components independent, whereas what we were finding in the 4-parameter parameterization that we used from the literature is that there was a lot of internal correlation between the attenuation curve parameters. OK, so this bit is done. And the next bit that we're working on now with Daglan is to, again, use constrained regression and try to essentially model these B parameters that ultimately depend on the IOB components based on observable global galaxy properties. So again, just to remind you what's the end goal is that from our modeling, if we have a given galaxy, we know its properties, we know its intrinsic spectra, we then are going to be able to say what's at least the range of attenuation curve that we should apply to this galaxy so that we can really make as consistent as possible observable spectra. OK, but I just want to conclude my part, essentially, going back to observations. So far, I've talked mostly about synthetic observations, so we kind of tricked you into thinking this was an observational talk, but it was not really. But we're also looking at data. And here you see essentially the first demo of a data catalog package that we're working on with Kartek-Iyer. And what we're trying to do is to have a new catalog of observations that will be used to calibrate simulations and analytical models. And we're really trying to do a very careful work in going through all of the literature and all of the references to really pick what is the most updated one and try to uniform binning, error handling, and everything so that, and really make it simulator friendly so that in principle, any simulator can then download this package with pip and then just readily run it and compare their simulation with observations, also obtaining best fit relations without really having to go through all of the papers and check what are the limits of a given survey and how the errors are computed and the pitfalls that come in there. OK, so I think I'm essentially going to stop here. I have some next steps, but I will give the word to Shivam.
Right. Thanks, Laura. OK, great. Yeah, so switching gears now to CMB. OK, yeah, so CMB is really great because effectively it's sensitive to the full observable universe, not just the surface of recombination. So as the light from the surface of recombination travels through the large-scale structure and towards our telescope, this light gets lensed through the large-scale structure, it gets scattered. So effectively, if you can extract it, it gives you a map of the full observable universe. Of course, the caveat is your instrument needs to have good enough resolution to extract the thing. So for example, if you take these amazing observations from ACT and try to look at the place where some galaxy is, you can extract various different aspects about the matter as well as the baronic components. So for example, if you look at the lensing of the CMB from the total matter distribution, you can make these plots of how exactly the total matter is distributed around the galaxy. If you look at this kinematic Sonev-Zeldovich effect, which comes from the scattering Doppler shift of the CMB from the bulk velocity of the electrons, you can extract how the baryon density is distributed. If you look at the scattering due to the thermal motion of the electrons, you can extract how the pressure is distributed. And then, of course, as Laura cautioned us, it's not, there are these dust grains also that emit in the same wavelength. So you will be sensitive to how exactly this dust emission is distributed around the galaxy. So basically, if you have some way of extracting CMB, does give you access to this aspect of total matter distribution as well as the baronic thermodynamics. And in this way, it's also highly complementary if you can jointly analyze with the galaxy observations, right? Because the way any statistics that you measure from these observations will be probing different sort of halo masses, different sort of redshifts compared to these same statistics that you extract from just the galaxy observations. So the main, one of the overarching goals of the learning the universe is to have some sort of joint inference of cosmology and astrophysics from both galaxy as well as CMB. And we will start off by jointly analyzing the data from BOSS and ACT. Okay, so what have we done in past few years is to try to come up with these sort of joint models and try to now bridge the gap between having the models and then going making synthetic mocks so that we can go and analyze the data. So the ingredients that go into creating a realistic mocks start from, of course, primary CMB, but that is the easier part. It's just a Gaussian random field. But then you need to have a proper way of lensing the CMB map, have all of these scattering effects that you need to add. But then, so research in this direction has been going on for past decades. But then some new things that as we analyze data at higher and higher resolution and higher order statistics, for example, you start being sensitive to various environmental effects, like, for example, how does the tidal shear and concentration of the halos impact these baronic thermodynamics, for example. Then you need to start folding in different observational properties, like how exactly the noise is there, beam of your of your telescope. But then the harder part that is still a work in progress, how exactly you fold in something like cosmic infrared background and also accurately model galactic foregrounds as well. So the things that are with green tick, we have some sort of handle on this. We are still working on packaging everything together so that we can create these nice mock catalogs. And the overall goal is to kind of go beyond running these large volume traditional hydrodynamical simulations, right? Because although they are extremely useful in kind of understanding if you have accounted for all of these model ingredients well enough, giving you a more physical picture, they are really slow. So you cannot actually run a lot of them and hope to do a proper implicit inference analysis as Greg and Laurence mentioned earlier. Okay, so the need is to have some sort of fast and interpretable way of running some cheaper simulations, and then have a way of going to these baronic components such that you can create the maps of these secondary anisotropies of the CMB. So this thing colloquially comes under this umbrella of baron pasting, and there are various groups that are working on it. So we try to interact with them, have their input, as well as develop the new things. And yeah, basically just to summarize in a way, we want to take these fast dark matter simulations and try to fold in these different astrophysical and cosmological effects while accounting for various secondary properties of the environment that can impact these different observables, such as environment and anisotropy, and have a self-consistent modeling of both galaxies and CMB. So towards this front, we are focusing on two different sorts of approaches. So first, one is this field level approach, where we take the full field of dark matter and try to have this mapping between dark matter and gas at the field level. And the other is this more traditional halo-based pasting approach, which requires identifying halos in these dark matter simulations and then pasting these baronic properties on top of it. But the whole pipeline that we are trying to develop to go from here to there is effectively modular. So if people have other methods that they would want to integrate, that could be done. Okay, so let's start off with the field level approach. So the first approach is this transfer function approach, where we start off with these hydrodynamical simulations, right? The Camel's simulations. And then we effectively try to see if you input the matter density field in your dark matter only simulation, can you relate it to the overdensity field of your gas or like distribution of electrons, right? And we try to see if the phases of these two distributions are preserved, you can easily relate these two with a simple scale-dependent transfer function. And as shown in this Sharma et al. Paper, as well as a paper led by Henry Liu, that this thing is true up to k of approximately 5 to 10. If you're looking at different statistics of the gas distribution, the baronified total matter distribution, as well as the thermal as the pressure distribution. So the way this whole approach works is we take these pairs of camel simulation where we have access to the matter distribution as well as the gas fields. We measure this transfer function over all of this suite of 2,000 simulations. We use Gaussian process emulator to have an emulator of this transfer function. And then note that this thing is a very small box, right? Like it is just a 25 megaparsec box. But then we try to see if we learn this transfer function in these small boxes, can it generalize to a significantly larger volume and some different cosmology and astrophysics, as is given by this Millennium TNG simulation, which is a factor of 10 bigger box size. So if you give it the matter density field in the simulation, can you extract off the gas in there? Before I show you the comparison, the second approach that members of the collaboration has worked on, as is given again in Henry's paper, is to use this hybrid effective field theory approach. And the way this approach works is that you say that whatever bias tracer that you're interested in, you will write down its bias expansion in the very high redshift Lagrangian field. And then instead of in the traditional perturbation theory approach using the loop expansions to solve for any statistics in the Eulerian field, you're going to use the n-body simulation to give you this evolution exactly. So basically what this comes down to in practice is that you will take all your different distribution of the particles in the Eulerian field, but then you will weigh them by effectively this weight function that you extract off in the Lagrangian field. And the upshot is that this thing has been shown to work at remarkably smaller scales compared to doing a traditional loop expansions. So for example, in here, you can see how both of these methods are working. So in here, I'm showing you the real tau field, which is effectively you can think of it as a projected electron density field in Millennium TNG, as has been trained by these approaches. On the lower left is the transfer function. So how this field looks like when you learn it through the transfer function. You can see that the match is really good. And then on the top is this hybrid perturbation theory approach, where either you use these bias functions as a function of scale, or you think of them scale independent. So in both cases, you can see the match is nice. But looking at it a little bit more statistically, here is the comparison at the power spectra level. So on the top right, you can see what the power spectra looks like of these tau fields in black from this large volume Millennium TNG simulation, and in red is the thing that you have input. And you can see that especially with the transfer function approach, but also with other approaches, you can get this suppression of the power due to feedback from dark matter to the electron quite well. And on the right-hand side, it's the same thing that's been shown for the Compton Y, so the pressure field. So till now, we have done this validation at the 3D power spectra level. So now we are working on actually taking this thing and creating mock maps. So like taking the projection of this 3D thing and projecting it down to 2D, so that we can create this thing as an observed 2D map. And the second thing that we have been thinking about and starting to work on is using some more machine learning methods to augment this correction, especially on the smaller scale. So you can think of it as a two-step pipeline, right? Like you can use these approaches to get the first stage of baronified or like your baronic fields going from dark matter, and then you can try to train some diffusion model or normalizing flow kind of model to then go from that to the actual field. So that will get the corrections on the smaller scales better. Okay, so moving on to the second part where we try to now use more halo-based approaches. So in here now we are trying to develop more consistent modeling of all these different probes that we are sensitive to in the CMB observations, right? So for this thing, we take this baronification approach, as has been pioneered by Schneider and Tessier, and we augment it or generalize it to now consistently predict not just the distribution of the matter, but also the baronic thermodynamics, as well as we fold in different stellar mass dependent HOD formulation, like in Alexey's paper, and try to have a consistent framework for galaxies, the baronic thermodynamics, as well as total matter. So in a nutshell, how does it work? Like you have in your n-body simulation, you have a halo of a given mass. You now come to your hydro simulation where you now have different components, and then you effectively conserve the mass in distributing the total matter in the n-body simulation to these different components. And you also solve for back reaction of having these different components on your dark matter. And once you have access to this, parameterized by some central set of parameters, you can use the hydrostatic equilibrium to get a handle on the total pressure. And then you can account for non-thermal support to get you the thermal pressure component. And basically, you can see that now you have all of these components. So with some central set of parameters, you can effectively connect all of these different probes together. So recently, we have used this thing in particularly joint analysis of cosmic shear from dark energy survey and the TSZ map from ACT. And using this formalism, you can see that we can get better constraints on cosmology. So for example, omega matter and S8 in black, you can see that our constraints on the cosmological parameters is better if you only analyze the shear 2 point, which is just the weak lensing power that is sensitive to total matter distribution. So adding in this consistent modeling framework and adding in baronic thermodynamics helps you there. But not only that, it also helps you in getting better handle on the total matter power suppression, so getting you handle on the astrophysics as well. But the nice thing is that now we have used this sort of model, and we have done some sort of model comparison with all the other frameworks that exist of doing this sort of consistent modeling, and try to see how physical this model is. So for example, in here, in this work led by Pranjal, what we have tried doing is try to take 3 different sort of models. So from Alexander Mead, Arico and Angelo, and then this Schneider 19 plus, that was the model that I was mentioning now. And taking this model to jointly fit different summary statistics. So the matter power, the matter cross pressure, different bound gas fractions, stellar fraction. And you can see that all of the 3 models work remarkably well in fitting these 3, right? But then you can you can go one step beyond. You can say that while they fit these summary statistics well enough, can I use these fits or the parameter inference to extract something physical out of them? For example, like, do they explain the actual 3D profile of the pressure, the temperature distribution, the electron distribution well enough? So you can see in the bottom panel, I'm plotting what the profile of these 3 baronic components look like in either group size halo or cluster size halo. And you can see it's the dashed line that matches with the actual simulations much better compared to other models. So this says that you can actually go and analyze your summary statistics in the data, and then actually trust the inference on the profiles. So to have a mock made out of this particular halo-based model, we need halos. So for now, we are relying on some sort of n-body simulation. So particularly this amazing effort by the Backlight group, which is running a 1 gigaparsec box at very high resolution, going down to very low halo masses. And then they take these boxes and then tile them up in a way to create full sky maps going up to approximately redshift of 3 and sampling 5 cosmological parameters like in Quixote to have access to approximately 1,000 simulations. So we are now working on pasting these different maps on these simulations. So within the collaboration, we have developed these more GPU accelerated ways of pasting things now, and also consistently pasting everything. So this is Jack's pasting example of taking the Halo catalog from one of these backlight simulations and consistently pasting in the matter field, the KSZ field, the TSZ field, and the Galaxies field. So now we are working on taking this suite and trying to do this sort of pasting and then hopefully doing inference in coming months. Okay, but then we need to also think one step beyond. So as I mentioned, like in the simulations, they take 1 gigaparsec box and then tile them up to create the full sky map. But that can create some non-trivial effects that can impact your inference of statistics. So for example, in this nice work by a student and Adrian, they have tried to look at how exactly different statistics can get impacted once you tile these boxes. So for example, in here, looking at the variance in different statistics, depending upon if you're looking at the line of sight that is most impacted by this tiling versus if it is not impacted by this tiling. And you can see that the variance is significantly less if you look at the line of sight that is more impacted versus less impacted, saying that you need to be careful about these super sample effects. So to this end, for example, the Half Dome team has been working on running these significantly larger boxes simulations so that you don't have to tile them up. But then you cannot run a traditional n-body simulation for this because it's going to be insanely expensive. So they have been using these FastPM simulation that Laurence mentioned. So these are very high resolution, large box simulations. And you can see that with these simulations and using the approximate halo finders, they can consistently now start pasting in the different observable probes. And this is at a single cosmology, but within the group, the LH set is also in the work, so we can try to interface with them and try to see how well we can do this thing with our models as well. But then looking again, like towards the future, we still need to make things faster, right? Like it could be that the number of simulations that we generate from these methods is not sufficient. So as I mentioned, like previously, even though the simulation is faster, it is still has a lot of particles. So still not as fast to run as many simulations as you want. So for example, in this nice work by Anirban, they have tried looking at how many simulations you might need optimally if you are looking at some sort of summary statistic to have converged posterior. So compared to the Kramer-Rao bound in the Fisher forecast for the matter power spectra, you can see that just 2,000 simulation is not good enough, and that does not get you the best posterior and a bunch of different cosmological space. You need to push to say 4,000. But then say you are looking at some other statistic, this number could differ. So you would ideally want to have a way so that you can actually generate these simulations on the fly. You can take some sort of low-res simulation that you can easily generate and have ways of generating or like pasting in things as fast as you can. So Laurence very nicely summarized different accelerated forward models using different techniques. And what that can hopefully get you is you can run these things on the fly, have n-body like halos on the other end, and use these GPU accelerated methods of pasting in different observables. And then try to consistently analyze them so that you're not then limited by this fact that you only have n number of simulations. Okay, so why is all of this effort interesting, right? Like from various observations in last few years, there has been these very convincing signatures that the feedback prescriptions that are used in the hydrosimulations might not be adequate. So for example, in this nice paper by Borian and Simone, they tried looking at the KSZ profile around the DESI-like galaxies, and you can see that the prediction of this KSZ profile, if you assume that gas traces the dark matter, disagrees with the measurements quite a lot. But even if you use something like TNG 300 kind of feedback physics, that also does not get you the right level. You need to use some very high feedback prescription. And there have been various other studies that have corroborated that recently. And this signature is going to get like significantly more precise in the coming years, like with having better CMB maps from SO, for example, having significantly larger galaxy sample from DESI and DESI2, and also, for example, looking at similar things from something like LSST and Roman. So we really need to have different models as well as approaches in our pipeline, so that we can probe this effect in a more consistent way. Okay, so just to end and summarize, for over the next year, our plan is to develop these different methods going towards the actual 3D observables to now create consistent mock maps and use these backlight simulations as well as the field-based techniques to actually do the inference and not only use traditional power spectral statistics, but also go to some higher order statistics with these CMB secondary maps. And consistently start working in integration with different accelerated forward model approaches. But then over the longer term, given the amazing team that we have within LTU and connecting it with Synthops people, there are other methods that are in work. For example, this amazing code Sapphire, led by Viraj, where they're trying to even more consistently and physically predict the galaxy observations as well as the CMB, the CMB observations. And with Laura, I think like as she mentioned, like dust is also another very major bottleneck that we need to pay close attention to. So that's also we have started to work on using these various semi-analytical model to consistently have maps of CIB as well. But yeah, I think like within next 3 years, we hope to make much better progress, have better physical models and accelerated forward models to analyze both of these data sets jointly. Thank you.